So solution stoichiometry is going to be basically the same as regular stoichiometry. You're still going to need the mole ratio and all that kind of thing, but when we're dealing with solutions, we wouldn't have a mass. Like when we did stoichiometry the first time around, we said if you had 15 grams of, whatever, you do the reaction, how much would you get? Well, if you're dealing with a solution, you're going to have a volume. So you would measure out a volume of that concentration. So that's what you're going to start the problem with. And these are some things that you need to remember. We talked about this on Friday. Volume times molarity is going to equal your number of moles of solute. Once you get to the moles of solute, then you can use your mole ratio and solve the problem stoichiometrically, just like we learned how, or most of us learned how, rather. And then sometimes if it's going to ask you for how much volume of solution you could create, you need to remember that moles of solute divided by the molarity is going to equal the volume of solution. And that's because I want to remind you that, remember, when you see molarity, your units are moles per liter. And so you can use that as a conversion factor as needed. You can either put moles on the top or you can put moles on the bottom. But your value that molarity is always going to go with moles because it's always per 1 liter of solution. So let's work an example. And someone needs to be my calculator today. And you'll all have them out, so you can't say you don't have a calculator. This one wants to know how many grams of silver will be formed by the reaction of excess copper with 208 milliliters of 0.1 molar silver nitrate. So the balanced equation is already there because that's what we always have to start with. And so we're going to just, whoops, I didn't mean to do that. Okay, so we're going to start with this right here because it's really the only thing we can start with is this right here. Okay, and remember, because molarity is moles over liter, our volume has to be in liters. Okay, and the conversion factor is 1,000 milliliters to a liter. And when I was grading some of the quizzes from earlier, a lot of people are still getting that conversion factor wrong. Milliliters are smaller than liters, so your value in liters should be much smaller. So I'm just going to do that in my head, and it's going to be 0.208 liters. And all I did was divide by 1,000 or move the decimal place over 3 times. So I'm going to start with my volume because it says volume times molarity is equal to moles of solute. So I'm going to say 0.208 liters. And then I'm going to multiply by the molarity that they gave me is 0.100 moles of AgNO3 over liters. So that cancels out my liters. Now that I'm in moles of silver nitrate, I can use the mole ratio from the balanced equation. So from the balanced equation, I need 2 moles of silver nitrate. Okay, and it produces 2 moles of silver because that's what it's asking for. 20 grams of silver. So I can balance out moles of silver nitrate. Now I'm in moles of silver and I need to get 2 grams of silver, and how do I do that? Molar mass. Okay, the molar mass of silver is 107.87 grams of silver per mole of silver. So then that cancels out. I need my answer in 3 significant figures because both of my values up there have 3 sig figs. So that's what I need to put my answer in. So someone do that for me real quick. I think it comes out to around 2 1/4 or something close to that. .24, I think that sounds right from this morning. 2.24 grams of silver is what can be produced from that reaction with that concentration. Okay? So we'll do one more before we move on to colligative properties. Is anybody still writing? All right, and this one, it's wanting to know what volume of copper 2 nitrate will be formed by the reactions of excess copper with silver nitrate, and now we have a different concentration. Okay, so we're still going to start with this right here, volume times molarity. This time we have 45 milliliters. If I divide that by 1,000, I get 0.045 liters. That's an L. Okay? So we're going to start with that. We're going to do volume times molarity. So we'll start with 0.045 liters. Going to multiply by the molarity of 5.20 moles of silver nitrate over liters of solution. So my liters cancel out. Since I'm in moles, I can go to my mole ratio. From the balanced equation, I have 2 moles of silver nitrate. And this time I'm looking for copper 2 nitrate, and I only have 1 mole of that from the balanced equation. And now it's wanting to know what volume of 3.5 molar copper 2 nitrate could I solve for. So this is where I can use that molarity as a conversion factor, and I'm going to flip it. So I'm going to, because I'm wanting to get rid of moles, I'm going to say 3.5 moles of copper 2 nitrate per 1 liter of solution. So now my answer will be in liters of copper nitrate. So someone do that math for me. I think I remember what that came out. I think it comes out to 0.033. Tell me if I'm right. Does it come out to 0.033?
Yeah.
Okay. And I need 2 significant figures because of that right there has 2. So it'd be 0.033. Make that where it's a little clearer. Liters, which would be 33 milliliters. So either one of those. Since I didn't specify if I wanted in liters or milliliters, either one would actually be okay. But the key is you have to take it, you have to make sure that when you do volume times molarity, you have to be in liters. Okay? So that's how you do solution stoichiometry. Very similar to regular stoichiometry. Instead of starting with mass, we're going to start with a volume and a molarity. And that's how you get to moles. Okay? So that brings us to colligative properties. And colligative properties are a unique kind of property. Remember in the beginning of the year we talked about physical properties and we talked about extensive or intensive properties. Well, this is a subset of extensive properties rather. Okay. First of all, when we're talking about colligative properties, they are characteristics of a solution that do not depend on the size or type. In other words, they do not depend on the identity, but they depend on the concentration. The more particles, the bigger effect on the property it'll have. Okay? The physical properties of the solvents are different than when we have a solution. So we're going to mainly talk about water. Water as a pure solvent behaves much differently than when I add a solute to it. Okay? So you guys know from experience, especially if you've ever been in colder climates, when it gets cold outside and they think the roads are going to ice, what do they put on the roads? Salt. And they do that because once they add salt to the water, what it actually does is it lowers the freezing point. And so then the roads don't freeze as quickly. And so that's an example. They don't just put a little bit of salt out there, do they? No, because they need a lot, and it's because the more concentration and the more particles that are in that solvent of water, the bigger effect it has. Okay? And so we care about the number of particles. Okay? So before we talk about what the 3 things are that are going to affect the colligative properties, we want to recognize how to determine how many particles are in something. However, I did leave this definition of colligative properties out, and I need you to add it into your notes. So you need to add this definition. Okay? And while you're writing that, quick show of hands, how many of you actually go back to your notes and study your notes before a test? Okay. Because a lot of people aren't, and I'm not giving you notes because I like giving notes so you have something to study. The review's not enough to cut it. You need to study your notes as well. Okay? Because so many times I can go look and see what's missed on the test, and I talk directly about that in the notes, and I'm like, it's in the notes. So then I'm much less likely to throw a question out if I know I addressed it in the notes too. So it's the solute's interference with the pure solvent's phase change that's ending up affecting their properties. It's messing with their phase change. Everybody have that? Good? Okay. So, let's talk about number of particles. When sodium chloride, remember ionic compounds, when they dissolve in a solution, they break completely apart into their separate ion particles. So we have to count up how many particles total that they form. And so sodium chloride would form 2 particles. 1, 2. Whoops. Well, that just went off. I thought I hit that button. So it'd form 1, 2, so it'd have 2 particles. The sodium sulfate breaks apart into 2 sodium plus 1 sulfate, so it would have 3 particles. And then how many would the next one have? 4. Okay? So when you have polyatomic ions, like this, and this, and this, they stay together. When they split up, they stay together as an ion. Okay? So I want to make sure you don't accidentally take it and break it into sulfur and oxygen, because they stay stuck together as one particle. Okay? If it is something that is covalent, or an organic molecule, and of course remember organic is like hydrocarbons, they have carbon and hydrogen, and covalent is 2 nonmetals, 2 or more nonmetals. They stay together as only one particle. They do not break apart because they don't ionize. We talked about that when we talked about solvation, and we said sugar is an organic molecule. It's also covalently bonded, and it stays together. It dissolves, but it stays together as one sugar molecule, not like the sodium, which splits apart. Okay, so when you see those, they only have one particle. So you have to take that into account on the effect that it's going to have on the property. Okay, so let's do a couple of these together just to practice. Magnesium chloride looks like this. I've done this all day. Magnesium chloride looks like that, so how many particles would it make? Now I'd make 3. Because when it breaks apart, you get magnesium plus 2 chlorines. So it would give you a total of 3 particles. Okay? How about aluminum sulfate, which looks like this? How many particles would it give you? 5. It would give you 5. Because you would get 2 aluminum and you would get 3 sulfate particles, so you would get 5. How about this one right here, ethanol, C2H5OH? How many particles would you get there? Nope, you would get 1. It's an organic molecule because of the carbon and hydrogen. Okay, so you'd only get 1 particle with that. What about dinitrogen pentoxide? How many particles would you get there? Also only 1. It's covalent, 2 nonmetals. Remember, covalent compounds give you only 1 particle. They do not break apart. So that would only give you 1 particle when you did that. So the only thing that are going to give you multiple particles are ionic compounds, which are metals and nonmetals. Okay, stuff that we learned last semester that we still need to remember. Okay, that's what makes this class a little bit harder. You got to keep remembering the stuff that we already learned. Okay. So the first type, I think this says it got left out in your notes, but I think I put it back in for y'all, is about vapor pressure. So one of the colligative properties is the lowering of vapor pressure. So when I add a non-volatile solute, it will lower the vapor pressure. And volatile means ability to form a gas. If it's very volatile, it goes from a liquid to a gas very quickly. Like gasoline, very volatile. It goes from a liquid to a gas very quickly. Okay? But when I add a solvent, a solute to it, it can lower that vapor pressure, meaning it will not go to a gas quite as easily. And the way it does this is this little mechanism right here. Normally, when you have evaporation, it's happening at the surface level. Okay, so the particles at the surface level are able to overcome the intermolecular forces and evaporate. Okay, but it's only the particles at the surface. The ones at the bottom can't evaporate until I get down to the bottom. But when I add a solute to it, now at the top of that, I don't just have solvent particles, I have solvent and solute particles. So that interferes with the ability or the how quickly something can evaporate. So that's how the solute works. And it does this by lowering the vapor pressure. So the red is what the curve for normally looks like. But then when you drop it down here, that's when it ends up changing your boiling point and it ends up changing your freezing point because of that vapor pressure. Okay? We will not do calculations of how much, but you have to recognize if I told you you have this sample that's got 3 particles and another sample that's got 10 particles, which one would have the greater effect? The one with 10 particles or the one with the higher concentration. That you do need to know. You also need to know that for boiling point, it's an elevation. Okay? Meaning it raises the boiling point. Okay? I'm not going to make you do the formula because we don't have to do any calculations with it. But in the formula, there is one of the components in there is called I, which is a Van't Hoff factor, which is number of particles. So you have to include that in your calculations, your number of particles. Okay. So if I add salt to water, it increases the boiling point. How many of you add salt to water when you make pasta? How much do you put in there? Just a little bit. It's wasted salt. Yeah. Because you have to put enough in there for it to have an effect. Because it doesn't matter that you're putting salt, it's the particles that you're putting in there. Okay? So, like when I make pasta, I take the cap off my shaker and I dump some salt in there. Like there's some salt in there. It's because the number of particle and the concentration is what affects the boiling point. Now, it actually, most people will tell you, I add salt because it makes the water boil faster. It actually does not make the water boil faster. It actually, the water will get to boiling at a slower amount of time because it's a higher temperature. But when you put your pasta in there to cook it, it's cooking at a higher temperature, so it cooks faster. It doesn't cause your pasta to cook faster, but the boiling point itself will also be raised to be a little bit hotter than 100 degrees Celsius. Okay. Also, according to Rachel Ray, that's your only chance to season the pasta. I don't know if that's true. Because that's when it soaks up the water. This light's down. Okay, so it raises the boiling point. But what did we say what does to the freezing point when the roads are getting icy? It lowers. It has the opposite effect on a freezing point. It's a depression. Freezing point depression. So you definitely need to know that it raises the boiling point when you add a solute, but it lowers the freezing point. Okay? The freezing point one is pretty easy for people to remember because we're familiar with putting salt on the road so it doesn't freeze. But most people don't realize it's actually raising the boiling point. So it actually basically takes that where their phase changes would normally be boiling and freezing. It kind of stretches them this way a little bit. Okay? So you don't have to do this because we don't do the calculations in here, but I do want to ask you this question. If I had this, okay, which one of those solutions, considering they're all the same concentration, which one of those solutions would have the highest boiling point? So I've added all these things to water. Which one of those solutions would have the highest boiling point? This one would have the highest boiling point. Okay? Because it has 3 particles. This one has 1 particle. This one has 3, and this has 4. I said it has 4 particles, sorry. So it would have the greatest effect on the boiling point. So the boiling point would be the highest for the aluminum chloride solution. Okay? Now listen closely to what I'm going to say, because this is where people get confused. Which one would have the highest freezing point? The highest freezing point? Sugar. Because sugar would have the least amount of effect on the freezing point, so it would have a higher freezing point. The aluminum chloride would have the lowest freezing point. So I want to make sure you understand how to look at that. Okay? So the worksheet that you picked up today is going to be due tomorrow at the end of class. Okay? So if you don't think you can finish it all tomorrow, I gave it to you today so you could start on it a little bit. Okay? If nothing else, you should answer the questions at the end since this lesson is fresh in your mind about boiling point, freezing point. And then I'll give the review out tomorrow. And then Wednesday in class, you have a review quiz to be done in class. And then Thursday's the test. And everybody knows Friday's a holiday, right?
We get off.
Yeah, you were off on Friday. Good Friday. You should be. It's Good Friday. Yeah, literally, it is Good Friday, so you should be. Yeah.